Okay, in this video I want to go over one of the more difficult textbook problems in chapter 3. So this is problem 31. So we have two finite sets A and B. In part A we have to show that if the cardinality of A is larger than the cardinality of B, then no function f from A to B is injective. For part B, we assume that the cardinality of A is less than the cardinality of B, and we want to show that no function f from A to B is surjective. So let's start with A. Looking at the problem, we see that the important characteristic of the function is injectivity. So let's go ahead and write the definition of injective. So if we have a function psi from x to y, psi is injective if for all x1 and x2 in x, we have x1 is not equal to x2 implies that psi of x1 is not equal to psi of x2. For this particular problem, I find this characterization to be more useful. And again, the cardinality of A is just the number of elements in A. The cardinality of B is just the number of elements in B. All right, so let's begin. Let's rewrite our assumptions. So we suppose A and B are finite sets such that the cardinality of A is larger than the cardinality of B. Let's assign a number to each of these cardinalities. So let's let n represent the cardinality of A, and we're going to let m represent the cardinality of B. So this allows us to rewrite A as a set containing A1, A2 through AN. We could say, let's order A as A equals A1 through AN, and order B as B equals B1 through BM. So we know that n is greater than m. Okay, now we're going to suppose towards contradiction that we have an injective function from A to B. Okay, so the general idea of this proof is that because we have more elements in A, we're unable to assign to each element of A a unique output in B. But the way that we actually write out this argument is a little bit more technical. That's why it's problem 31. It's at the end of the chapter. It's not an easy problem. So what I'm going to do is I'm going to define a new set. So I'm going to define BK to be the set f of A1 through f of AK. For each k that's between 1 and n, which is the number of elements in B. So note, because each of the A1s through AK is distinct, then f of A1 will be different than f of A2 through f of AK, or maybe it's better to say f of AK will always be different than f of AL for L less than K. So we have this nice nesting of the sets. So we have that B1 is a proper subset of B2, which is a proper subset of B3, and so on until we get to BM. Now, also note that the number of elements in B1 is 1. It's less than the number of elements in B2, which is 2, and so on until we get to Bm, which has m elements. But since B has m elements itself, we know that Bm must be equal to B, because there's only one subset of a set that's going to have all of the elements in the set. So how do we reach our contradiction? Well, we still have to assign a function value to am plus 1. So we know, because B is the codomain of f of am plus 1 is in B, which is equal to Bm, right? So I'm just gonna, you wouldn't need to write this in your proof, but just to remind you what Bm is f applied to A1, f applied to A2, and so on until we get to Am. So if f of am plus 1 is in B, which is equal to Bm, what that means is there's some value of k, which is between 1 and m, for which f of am plus 1 equals f of ak. So we know there exists k in the set 1 through m such that f of am plus 1 equals f of ak. So in other words, ak is not equal to am plus 1, just by construction, right? The elements of a set have to be unique. But also, so we have this and, f of am plus 1 equals f of ak. So this contradicts our assumption that f is injective. And therefore, no such injective function can exist. Okay. Now, why don't we look at the proof of B? So remember, first also put the little box when you end the proof. So B, now we assume that A has fewer elements than B. And we want to show that we can't construct a surjection from A to B. So here the important definition is surjective. So let's just recall that definition really quick. So recall that a function from x to y is surjective if and only if, for every y in y, there exists x in x such that psi of x equals y. Okay. So this proof is a little bit more complicated than the injective case, but we're going to do a proof by contradiction again. So just to make things a little bit to make the explanation a little more quick, we're not going to rewrite everything that we just wrote. But let me say, we're going to label the sets A and B identically as we did before. So we're going to assume, or we're going to label A as A1 through AN, and B as B1 through BM. But this time, N is going to be less than M. So we're going to suppose we have some surjection from A to B. And we're going to reach a contradiction. So how do we do this? Well, what we know, because f is surjective, is that if you give me some bk in B, then I can find some aik in A, such that f of aik equals bk. So for every k between 1 and m, there exists ik between 1 and n, such that f of aik equals bk. We're going to do something similar that we did in the last proof. I'm going to let ak be the set ai1 through aik. And we have a similar nesting of these sets again. So we have that A1 is a proper subset of A2, which is a proper subset of A3, and so on until we get to AN. Moreover, the size of A1 is 1, which is less than the size of A2, which is 2, and so on until we get that the size of AN is going to be n. Okay. But by the exact same argument that we made in the last one, we know that A only has n elements. Each element of AN is contained in A. There's only one n element subset of a set with n elements. Let me put this as a proper, not a proper subset. This is just a subset of A. So we know that AN equals A. So remember, the way we constructed these elements A sub I sub k is such that f of A sub I m plus 1 is equal to B sub m plus 1. Okay? Right, but since A is the domain of F, we know there exists k in the set 1 through n, such that ai sub m plus 1 equals ai sub k. So what this means is that ai sub k, bk, it's a tuple of these two, is in F when we treat it as a function, as a binary relation on the sets A and B. But also, A sub I sub k and B sub m plus 1 is also going to be in F. So these two, B sub k and B sub m plus 1, are not equal. So we have that F is mapping the same element to two different things. So this contradicts the assumption that F is a function. And that essentially concludes the proof. Maybe you would add one more sentence like, thus, no function f from A to B is surjective. So these proofs are quite tricky, but I think it would not be a bad idea to study them. And I think that this particular problem is really good because it relates to some of the reasons why we study injective and surjective functions. I think it most cleanly relates to the idea of how the properties of a linear map or a matrix, what we study in linear algebra, relate to the number of solutions to a system of linear equations. So hopefully before the end of break, I'll have some relatively basic video about that. But in the meantime, if you have any questions about this particular problem, please let me know.